Alright, so we're going to solve some lens problems using the thin lens equation. So this example has three different parts. The first one a converging lens, second one a converging, and then the third one is a diverging lens. And so the object, there's in each case a 2 centimeter object, and it's placed either in front of the focal point or behind the focal point. So let's take a look at the first one, and we'll go back to the diagram of a converging lens, and I can kind of talk through what that diagram is showing us in the process. All right, so we have a 2 centimeter tall object 40 centimeters in front of a converging lens with a 20 centimeter focal length. So let's remember those numbers, and we'll go back to converging lenses. All right, so 40 centimeters is the object distance. So D0 here, or DO technically, it's an O for object. DO is the object distance, and it's 40 centimeters in this case. The focal length of this lens is 20 centimeters. Now, these lenses are symmetric, the ones that we're looking at, converging or diverging, and so they have a focal point on either side. And so this focal point is 20 centimeters away. So that means this point is 20 centimeters from the center of the lens. This point is 20 centimeters from the center of the lens. But the object is 40 centimeters away. So it's outside of the focal length of the lens in this case. So we're dealing with this scenario over here. So what do we expect? We expect the image of this object to end up over here. And that's an inverted real image. Now what that means is that the light from this is converging at this point over here, and the light is really going there. So when we say it's a real image, that means if I follow this ray of light goes into the lens and then is directed through the focal point and ends up here. So there's light really going to that point, and the same thing is true with this beam or this ray. It leaves here and it really is directed here. So if I put a piece of paper here and the object was shining light, you could actually capture this image on the piece of paper. Light is really going there. And it's inverted because it's upside down. Okay? And so the other things in this diagram, HO is the object's height, HI is the image's height, DI is the image distance, and F is the focal length. All right, so that's the diagram of the scenario. The equation we're using is the thin lens equation. That's over here on this slide. So this is the thin lens equation, or so I think your book just calls it the lens equation, but it technically is only really accurate when the lens is very thin. In all the examples we do, we can assume we have a thin lens. And so what it says is 1 over the focal length equals 1 over the object distance plus 1 over the image distance. So fairly simple. 3 different variables that we could be plugging in, and in any problem you could be solving for any one of those 3. What does make it a little bit tricky is that sometimes these numbers can be negative, and that's what we have this table here to keep reminding us of what quantities could be negative. So we have a converging lens. The object distance was 40 centimeters. The focal length was 20. So we're in row 1. The object distance is greater than the focal length. And so our image distance should come out positive. The height of the image should be negative, meaning it's inverted and it's upside down. And the magnification would be negative, which also means that the object is upside down. Okay, so what happens when we actually plug into this calculation? All right, so we're looking here at part A. Maybe I can make this bigger. Get rid of that. Okay, so here's our object. It's 2 centimeters tall, 40 centimeters away from the lens, and the focal length is 20 centimeters. We have 20 centimeters here, 20 centimeters there. And the dashed line, I usually use a dashed line to represent the optical axis. So that's the line that's parallel, runs right through the center of the lens. Okay, so object distance is 40, focal length is 20. That means I have 1 over 20 equals 1 over 40 plus 1 over di. And so because the numbers here are nice round numbers, the quickest way to solve it, at least from my perspective, was let's multiply through everything by 40. So 40 over 20 is 2, 40 over 40 is 1, and 40 over di I can leave as 40 over di. And let's make this a little bigger. You can solve for di, and you get di is 40. So if I put the object here 40 centimeters away, the image distance will also be 40 centimeters. And when we have a positive image distance, that means it's on the opposite side of the lens. So the light's leaving here and ending up over here. That's a positive image distance of 40. Okay, I can also calculate the magnification. In the magnification formula, you can use either set of variables here. If you know the image height and the object height, you can plug those in. Or if you know the image height and the image distance and the object distance, you can plug those in. And that's the information we have right now. We just solved for the image distance, and we can plug in the given information for the object distance. So we end up with minus 40 over 40, which is minus 1. So we found a positive image distance of 40 and a negative magnification of minus 1. So it's inverted over here. It's 40 centimeters away, so it's just as far away as the object was, but on the opposite side, and it's upside down. So in this case, that's where it ends up. The image would be over here, inverted. The same size, but inverted. Okay, and that makes sense with the table. The image distance is positive, the image height is negative, and the magnification is negative, so it's flipped over. Okay, second question. 2 centimeter tall object again. It's 10 centimeters in front of a converging lens with 20 centimeter focal length. So here we have this scenario where the object is actually within the focal length. So it's in here. It's closer to the lens. And in that case, when we trace out the beams, so this ray leaves the tip straight in and then heads through the focal point. This one straight through the center. They don't converge on this side. They actually converge back here. You imagine those lines connected back here and emanated from this point. So if you were standing over here and looking through the lens, it would appear to you like these rays of light left this point right here. And so that's where we perceive the image to be. Okay, so what do we expect in this case? We expect the image height is bigger, so it gets magnified. If you have a converging lens and you put the object within the focal length, it gets magnified. So this is how a magnifying glass literally works. You take something and you can put it close to an object and it magnifies the object. Just as a little trick, you can try this at home. Fill a bottle with water. The bottle will actually act like a lens because it refracts light. Water refracts light similar to glass. And hold the bottle close to some writing on a piece of paper, and you should see when you get the bottle close enough, it will actually magnify the writing. All right, and the image distance will be over here. So it's on the left on this diagram. The image is on the left, the same side as the object. So the image distance is going to be negative. It's a virtual upright image in this case. All right, so back to the formula. The formula is the same, but now we need to plug in the numbers. So I'll have 1 over focal length, 1 over the object distance, and now that's 10 instead of 40. Okay, so now here's our scenario. The object is closer, 10 centimeters. So we plug in 10 here. The only difference in these two formulas is now my object distance is 10. I'll solve it in basically the same way. Nice round numbers chosen here so that we can just multiply through by 20 this time. So 20 over 20 is 1, 20 over 10 is 2, and then we have 20 over di. So 2 plus something equals 1, right? That means this number here has to be a minus 1, which means that di has to be minus 20. Okay, then we can take that, plug it into the magnification formula. So our di goes on top, and it's a minus, so plus 2 magnification. So it's doubled in size. When you have a magnification of plus 2, it's doubled in size. So plus means it's upright, and the number tells you how many times it's magnified. All right, so back to the table. Our object distance was less than the focal length, so we had a negative image distance and a positive image height, positive magnification. Okay, on to the last one. Now we have a diverging lens, and we only have one scenario here for the diverging lens, so let's see which one it is. Oops, wrong page, this one. Okay, diverging lens, 15 centimeters in front of a diverging lens with a minus 30 centimeter focal length. So it's 15 centimeters, 30 centimeters, so it's within the focal length. We're in this scenario. So focal point's here, the object is inside. So the distance from here to here is 30, and this distance is 15. I should point out that for diverging lenses, the focal length is considered to be a negative, so it's a negative number. The way that you can use the same formula for all of these is that sometimes the numbers end up negative, and in this case, the focal length is actually negative for a diverging lens. All right, so we plug the numbers in the same way, except for now focal length is negative. So we have 1 over negative 30 equals 1 over 15 plus 1 over di. Solve it in the same way. So I multiplied through here by negative 30, and this became 1, this became 2, and then I can solve for di, and I get image distance of negative 10 centimeters. Again, take that, plug it into the magnification formula, and we get a magnification of 0.67. So it's actually reduced in size. So when you take a diverging lens and you bring the object within the focal length, you end up with a upright image, so it'll be positive, but it will be smaller than the original object. Okay, so that's a quick tour of how to use the thin lens equation and find the magnification. The key thing to remember is that these things have signs to them. They're either positive or negative, and the table on this slide can help you, so you don't have to memorize them. You can just refer to the table as needed, and things should work out.